Dear students, I welcome you for the today's lecture related to the experiments of heat transfer operation. Today we are going to discuss the Stephen Boltzmann apparatus, the plate heat exchanger and the shell and tube heat exchanger. So this radiation experiment in which the Stephen Boltzmann apparatus is provided with us and for which we are going to calculate the Stephen Boltzmann constant. Now this is the simple apparatus that is shown in the figure. Now the hot water that is coming inside the annulus section of a black body, black surface, and by the radiation of this black surface we are going to calculate the temperature of this disk. So how much amount of the heat that is radiated from this black surface and which is absorbed by this disk. So in this experiment we require to note down the temperature of this disk. This disk absorbs the heat by the radiation from the hot surface. So there is a hot or the heating vessel on the top of this experimental apparatus. From there, the hot water that flows into the annulus section, there is the one covering or one another vessel. Inside this vessel, there is a black surface which is available. Now this hot water, which is say around 80 to 90 degrees Celsius, is maintained inside this, and this vessel is insulated completely, so that we are assuming the no heat losses. So this vessel, outer vessel, is completely insulated and we are trying to maintain the constant temperature in this of water in this annulus section. So I am putting the 80 to 90 degrees Celsius water inside this, and the level which is indicated by this manometer, single leg manometer, you can note down whether it is completely filled or not. And there are the temperatures which are available on the inner vessel, T1, T2, T3 and T4. And from these four temperatures, we will take the average temperature of this black body. Now this black body will be say around 75 degrees Celsius. If I am putting the 80 degrees Celsius temperature inside that, it will attain certain temperature and it will remain say at a 75 degrees Celsius. Now this 75 degrees Celsius surface temperature of the black body will radiate the heat towards the center and will be accepted by this disk. As the temperature starts increasing, I am going to note down the temperature T5 for this disk. So this is the Stephen Boltzmann apparatus experiment, which we are going to calculate the Stephen Boltzmann constant. We are going to note down the temperatures of the T5, that is the disk temperature, and the time in seconds, so that we will be plotting a graph for the change in temperature with respect to time, the temperature against the time, the graph that is to be plotted. On the x-axis it is the time, on the y-axis it is the temperature, so that the graph will be like this. Then I am going to plot a graph, that is dt upon dt at time t equals to 0. That means for time t equals to 0, I am going to take the slope for this line, and the parameters related to the disk that is mentioned, that is mass of the disk is 0.006 kgs, cp of the disk that is given, area of the disk that is mentioned. T1 to T4 are the temperatures of the black surface for which we are taking the average temperature, and so the amount of the heat that will be transferred is the mcp into dt upon dt at time t equals to 0 upon a into ts raised to 4 minus t5 raised to the 4. That is, it is the fourth power of the temperature. So finally I am going to calculate the Stephen Boltzmann constant. Now the next experiment is the plate and heat exchanger. Now this plate type heat exchanger looks like this. There are number of plates, one plate, second plate, third plate, fourth plate. In our experimental apparatus, there are 6 number of plates having the specific length and the width of that plate. This is the industrial scale apparatus, so that is why there are so many number of plates. Then there is a fixed base plate and the moving plate that is available. Now inside these two rigid plates, the number of small plates that is available. In these small plates, the heat exchange will take place. So these are my small plates which are having the corrugations and the direction for the flow that is also mentioned. Now there is the some inlet which is provided and one outlet that is provided for cold fluid, and there is second inlet for the hot fluid and the second outlet for the hot fluid. So for hot fluid, one inlet and one outlet; for cold fluid, one inlet and one outlet. So when there is a heat that is exchanging, on one side of the plate there is a cold fluid, on the another side of the same plate that is the hot fluid that will be there. So in between, the across a plate, on one side it is a hot fluid, on the another side it's a cold fluid. So there is an exchange between the heat, and there are number of plates which are available in a single plate heat exchanger. So hot fluid which is entering from this side, it is specifically designed with the certain gaskets so that it will not enter in this plate. It will only enter in this plate. Similarly, the alternate plates, the hot fluid and the cold fluid that will be there. So this is what the flow arrangement, that is, you can see the hot fluid which is there on this side. The hot fluid is there, red is showing the hot fluid and blue that is showing the cold fluid. This is the total assembly for your plate type heat exchanger. Now in this experiment we are going to perform the calculate the heat transfer coefficient in a plate heat exchanger. So coming to the calculation part of a plate heat exchanger, to study the heat transfer in a plate type heat exchanger and to calculate the overall heat transfer coefficient. So certain hot water fluid that is available and a cold water fluid that is also available. So hot side fluid and cold side fluid, two fluids are there. I am going to start the cold water flow rate initially. Hot water flow rate is started after the establishment of the cold water flow rate. In general case, whenever you are going to start a heat exchanger, irrespective of a plate type or it is a shell and tube, one has to start with the cold side only. So with the help of a rotameter, I am going to adjust the water flow rate on the cold water side, for which I am going to measure the temperature, inlet temperature, and I am going to measure the outlet temperature. There is a one inlet and one outlet temperature for the cold water side. So at the entrance and at the exit of the plate heat exchanger, I am going to measure these two temperatures. In general case, the water which is around 25 to 30 degrees Celsius, that is the cold water temperature. And the outlet temperature, that will depend on the flow rate and the temperatures of the hot water side. So I have adjusted the water flow rate say to 100 liters per hour with the help of a rotameter knob. Then I am going to start the hot water side with the for the heating purpose. I am having a separate tank which is the provided with a heater and the pump is connected to that. So from the pump and through the rotameter, I am going to adjust the hot water side flow rate. Say 120 liters per hour is my hot water flow rate. I have adjusted the temperature to the of the bath to the say 60 degrees Celsius. Then this I can measure initially in the bath also, hot water tank also. Then I can start the pump so that the hot water side, that will be also in a rotation circulation. The flow, hot water flow will be in circulation. So I am going at a steady state, allow it for a certain time so that the steady state temperature that will be attained. This is most important thing while performing the experiment. You have to allow it for a certain time so that the system will attain the steady state. So I have started with a 70 degrees Celsius, 60 degrees Celsius and with a flow rate of 120 liters per hour. Certain hot water temperature, outlet temperature, that will be noted. Similarly, I am going to change the water flow rate from 100 to 150 to 200 liters per hour. And correspondingly, I can either keep the water flow, hot water side flow rate to the 120 only, or I can even change the hot water side flow rate and take the readings for the hot water inlet and hot water outlet. The total number of plates are there 6. Then length of the plate and the width of the plate that is mentioned. Then Cp of the water, density of the water that is also mentioned. So coming to the calculation part. So Q, which is you are going to calculate the overall heat transfer coefficient. First is the QH, which is equal to mCp into delta T H. Similarly, QC, that is mCp into delta TC. This is the water flow rate is mentioned in liters per hour, so you can change it to the mass flow rate. So both the mass flow rates, and mCp delta T is nothing but your mass flow rate. Then the area, number of plates, length and the width of the plate. Log mean temperature difference is the temperature across temperature differences for the hot water side and cold water side. Then delta Ti and delta Thi minus Tco upon delta To, which is equal to Tho minus Tci. So after calculation of all these parameters which you require in case of the calculation of the overall heat transfer coefficient, Q, that is nothing but your average for the cold fluid and for the hot fluid, QH for the hot fluid, QC for the cold fluid. So this is the value of the Q. A is the area for heat exchange. Delta Tm is the log mean temperature difference. From here you can calculate the overall heat transfer coefficient for a plate type heat exchanger. Now coming to the next experiment, that is a shell and tube heat exchanger. The shell and tube heat exchanger, it's a small apparatus which is available in our laboratory. That is a geyser, two geysers they are provided to increase the hot water temperature. That is our household geysers that works there to increase the or to supply the hot water. So hot water inlet fluid that is there and the hot water outlet fluid that is there. So here the another side, that is the shell side, is the cold water inlet. This is your shell side, cold water inlet, and shell side cold water outlet that is available. The tube hot water inlet and the hot water outlet that is available on the tube side. So the hot water fluid that will enter through the tubes, there is a pass partition plate, the pass partition plate will be on this side. Here the fluid that will flow like this, and it will change its direction from here to here, and the fluid which will be moving out from here, that will be taken out from the outlet. Now I am having the temperature measurements for T1, T2, that is for hot water inlet and hot water outlet. Similarly for cold water inlet T1 and cold water outlet for T2. So these are the temperature arrangements that is provided. So similarly, the performing the experiments, you have to adjust the different flow rates, that is the shell side flow rate and the tube side flow rate. For tube side flow rates, it's the hot water that is provided. I am going to adjust the flow rate, say 100 liters per minute. I am going to measure the inlet and the outlet temperature for the tube side, which is the hot water side. And for shell side, which is the cold water side, the flow rate is say adjusted to 75 liters per hour, and its inlet temperature and the outlet temperature that is also noted. The dimensions for the tube, that is the OD for the tube is 16 mm, ID for the tube is 13 mm. Then the pitch arrangement that is provided, number of tubes are 24, and the length of each tube, that is 500 millimeter. This was data that is provided for the shell and tube heat exchanger for the calculation of the heat exchange area. So here we are going to calculate the log mean temperature difference, effectiveness, and overall heat transfer coefficient that is to be calculated. So from the different resistance, I am going to calculate the overall heat transfer coefficient U0, then the log mean temperature difference. This is the formula THO minus TCO minus THI minus TCI upon ln of THO minus TCO upon THI minus TCI. This is the log mean temperature difference that is to be calculated. That is what the LMTD that is mentioned. Then for heat exchange effectiveness, this formula, that is the Cc, heat capacity for the hot fluid, and the C minimum, heat capacity for the either the cold fluid or the hot fluid, whichever is there, MCP.